Okay, so we're going to start chapter 6, and we're going to talk about circular motion. So far, everything that we've been doing in this course mostly has been in a straight line kind of motion. A car going down a street or throwing a ball up in the air and coming back down. We haven't really dealt with anything that goes in a circle too much. Let's just talk about a few things here. The frequency, period, and linear speed. Okay, so we have this relationship here between the frequency, which is how many events or cycles happen per second, and the period. The period of motion is, we're going to use a capital T for that because it's a specific amount of time, not just any generic time, little t, but capital T specifically tells us that it's the period of motion. And the period of motion is how long it takes for one cycle to occur. Okay, so frequency and period are complete reciprocals because if something happens more frequently, then it takes less time for each thing to happen. Okay, so let's go on a little bit here. And the units for frequency, let's just talk about that quickly here. So the units for frequency, they are cycles per second, but cycles isn't really a unit, so it's really just 1 over seconds, or we can call this hertz, Hz for hertz. Okay, so, but we do want to know that it's 1 over seconds. And then what would be the unit for period? And if you answered seconds, you are correct. All right, so this is going to be in seconds. Frequency is in 1 over seconds. Okay, so let's look at a situation where we have some object moving in a circle and it has a constant speed, but note, it does not have a constant velocity. So just take a moment and pause the video and see if you can determine why it is that the velocity is not constant, even though the speed is constant. Pause now. So the answer is that because velocity involves not only the magnitude, but also the direction, the velocity is always changing because the direction is always changing. As we move around the curve, the direction that we move keeps changing. So if we have a constant speed, let's go over to this expression over here to the left. We see that in general, we know that the average speed is going to be the distance covered over the time that it took to cover that distance. So if you were calculating your average speed to get to Hack from home, you would just figure out, okay, how much distance did I cover? How long did it take me? And you can determine what your average speed is. Well, we're going to do the same thing here, except in this case, the distance traveled, let's say that it goes around 1 time. Okay, so as this ball goes around one complete path and it comes back to its starting position, the distance traveled is going to be up here. This is the circumference of the curve, right? So 2 pi r, that's going to be how much distance is covered in that circular path. And then the period is how long it takes for that one rotation to happen. So this is a really handy expression for us to figure out the speed of something that's going in a constant speed circular path. One of the things that we're going to apply that to coming up in a later lesson is circular orbits. So we're going to be looking at the orbits of planets and even stars. Okay. So let's talk about centripetal acceleration and centripetal force. Okay, so the word centripetal, you may have seen, the book may have mentioned that the word centripetal means center seeking. So centripetal acceleration means that it's an acceleration that points toward the center of the curve. So if we go back up to this picture up here, we can adjust and we can put on the acceleration and show that, let's get a color that's going to contrast here. Okay, so here, the acceleration, the centripetal acceleration points toward the center of the curve. And it's this centripetal acceleration that is required in order to make a path curved. Because if we don't have any acceleration toward the center of the curve, then we're just going to move in a straight line and have no change in our direction. Okay, so centripetal acceleration is given by this expression here. So anytime we have a curve path, there's got to be something that is causing an acceleration toward the center. Now, keep in mind, I'm not saying that the object moves toward the center, but I'm saying that the object has an acceleration toward the center. Its velocity is still going to be in the direction of the curve path. But it's that changing, it's that acceleration that changes the velocity so that we don't keep going in the same direction all the time. Okay? So this v is the speed that, it's the same speed that we were talking about earlier up here. It's the same speed. It can be written in these two different ways. And so if we go down to Newton's second law, okay, so we're used to Newton's second law being that the sum of the forces equals the mass times acceleration. Well, now we're going to say, well, the sum of the forces in the centripetal direction is going to be m times the centripetal acceleration. Well, we know what the centripetal acceleration is. We have it up here at the top of this page. So we're just going to say that it's m times v squared over r. So I'm just taking that centripetal acceleration from up here and I'm plugging it in down here. So it is totally fine if you want to start your Newton's second law right here at this point. You don't have to go start with F equals ma and then substitute. You can start with the sum of the forces in the centripetal direction equals mv squared over r, and that can start as your template.